Hello everyone from Math 1340, Statistics. It's Professor Winston here again with a video on your KnewtonAlta homework. This is homework from Chapter 3. The reason I called it a KnewtonAlta section is because it doesn't specifically have a corresponding section in the Statistics OpenStax.org book. I did refer you to the OpenStax Pre-Calculus book, section 11.5 for this, but because this is all tied together with the Chapter 3 material, calling it the Chapter 3 KnewtonAlta section, Counting Principles. Alright, so we're just going to learn in this section different ways of counting numbers of possible outcomes. Now you were already introduced to the fundamental counting principle in section 3.5. When you went over the tree diagrams, they also talked about the fundamental counting principle. That's coming back here. That's also reintroduced here in this section. But then we have another couple things that we need to learn about too. Right, so one of these is called counting with permutations. So again, I don't know what permutations are, what any of the symbols means, so I'm going to click on More Instruction. The first time you come across an objective. Alright, so we're going to be counting numbers of ways of rearranging things. That's what a permutation is. So, many interesting probability problems involve the use of counting principles, permutations, and combinations. In these problems, we will use permutations and combinations to find the number of elements in events and sample spaces. In this section, we will learn how to count permutations. A permutation is an arrangement of a set into a particular order. Those are very important words. Particular order. So what you're going to see is that for a permutation, order matters. The order in which elements come in matter. And later when we talk about combinations, the order will not matter. Order doesn't matter. But here, permutations, order matters. The set of all permutations of a set includes every possible order, and order matters, of its elements. So for example, the number of permutations of a set of size n is given by n factorial. Alright, so I want to talk about what that is in a piece of paper here. You may have seen this symbolism before, but this is called, it's also brought up in another objective, but I'll just write it down here. It's called the factorial symbol. N with an exclamation point after it. This is n factorial. This is just a shorter way of writing the following. It's the integer n times n minus 1 times n minus 2 times all the way down to 1. So some examples, like say 5 factorial. Right, 5 factorial would be 5 times 4 times 3 times 2 times 1, which is, if you multiply all those, that's 120. Right, so the number 5 factorial is 120. 4 factorial would just be 4 times 3 times 2 times 1, that's 24. 4 factorial is 24. 3 factorial is just 3 times 2 times 1, that's 6. 2 factorial is 2 times 1, that's 2. 1 factorial would just be 1. Right, so 1. And then if we follow this pattern, we can state what 0 factorial is. Right? So you see what happens here. Right? To go from 5 factorial to 4 factorial, I just simply divided by 5. Right? Divided by 5. To go from 4 factorial to 3 factorial, I just divided by 4. To go from 3 factorial to 2 factorial, or just divide by 3. And get rid of that 3. To go from 2 factorial to 1 factorial, I would divide by 2. So if you continue with this pattern, you can now state what 0 factorial is, and this is defined to be, again, if I follow this pattern, I divided by 5, by 4, by 3, by 2, divide by 1. Divide the previous result I had by 1. 1 divided by 1 is 1. So please keep this in mind. This is important to remember. Many people find this confusing. When you see 0 factorial, it's 1. It's not 0. And again, I kind of like to do this and point out if you follow this pattern, it'll make sense, hopefully. All right, and then you can't divide by 0, so we're not going to go any further than that. All right. Now, if you'd like to also see this, if you have a calculator, let me show you the. I have the 84 plus. All right. Turn it on. Let's get rid of that. Right. If you have a calculator, where do you find this factorial symbol? And that's, you hit the math button. This is 83 or 84. If you have something else, Google how to do it. And then if you move over to where it says PRB, and you see number 4 there, it has the exclamation point next to it. But you can't just enter that. You have to enter what number you want first. So like if I go 5 factorial. So 5, hit the math button, go over to prob, hit the number 4. See 5 with the exclamation point. And according to what I've written here, it's 5 times 4 times 3 times 2 times 1. That's 120. Right. And as I said, even your calculator has it entered in 0. Right? 0 factorial is 1. Right? Defined to be 1. So be careful with the 0 factorial. All right. So this is factorial notation that they're mentioning here. So the number of permutations of a set of size n is given by n factorial. So for example, consider the set with elements a, b, and c. Since there are 3 elements, there are 3 factorial, 3 times 2 times 1 ways of rearranging them. There are 6 permutations, and they write them here. A then b then c, or a then c then b. Right? A different order is a different permutation. B then A then C, B then C then A, C then A then B, C then B then A, right? There are 6 different ways to rearrange 3 different looking objects, like A, B, and C. And that really comes from the fundamental principle of counting. So if you recall the fundamental principle from last section, if I'm trying to rearrange 3 objects, think of 3 slots, 3 processes, where I rearrange the first object, and where I pick the first object, then I pick the second object, and then I pick the third object, right? And my objects, say, are again A, B, and C. So I pick the first object. How many choices do I have? I have 3. 3, and then multiply that by, again, remember that fundamental principle of counting. If I do one process and then another process immediately after, and then a third process immediately after that, the number of possible outcomes, the number of ways that could be done, is just the product of the number of ways each process is done individually. Now if I picked, now say I pick a letter, A, I put A here. That means I don't have A anymore to choose from. So then the second choice, my choice of the second object, or the second position, there are now only 2 choices left. So time 3 for the first choice times 2 choices in the second process. And say that was the C. So now C I can't choose, and I can't choose A, and then the third object I would only have one choice left. So you see that's the 3 times 2 times 1, the 3 factorial. So there are 6 permutations, 6 rearrangements of the 3 objects A, B, and C, and that's all using the fundamental principle of counting. All right, so notice here that we count each rearrangement of the same items as a different permutation, right? A different order is a different permutation. That is, we count, A then B then C, and C then B then A as 2 different permutations, even though they have the same elements, right? They both have A's and B. They have an A and a B and a C in it, but they're in a different order. All right, the number of permutations increases quickly with set size. For example, if we increase the set size to 10, the number of permutations increases to 10 factorial. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 3,628,800. Right? The factorials get very big very fast. All right, so they define again a permutation. A permutation is an arrangement of the elements of a set, right? An arrangement in a particular order. Order matters. Right. So the first example. 7 city buses arrive at a bus garage around the same time each night. How many different ways can the buses return to the garage? So, how many choices do you have for the first bus to return? 7. Then how many choices would you have for the second bus that returns? 6. Then for the third bus, 5 choices. Then 4 choices. Then 3. Then 2. Then 1 choice for that 7th bus. So the total number of ways they can return is 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 7 factorial, or 5,040 ways for the buses, different orders that the buses could return to the garage. All right, at times, we will want information about specific permutations of the set. For example, we may want to know how many permutations of the set A, B, C have B as their second element. Now you can use this list here as they did before, and the ones with B as the second element are this first one and this last one. There's 2 of them. And we can quickly see that 2 of the 6 permutations have B as the second element. What would we do if we had 10 elements? Would you want to list all 3,628,800 possible permutations? No way. So how would we learn anything about certain subsets of permutations? So lucky for us, there is a mathematical way to determine how to select a certain number of items from a set and examine the permutations that result from that selection. All right, so this is a little formula here, and I'll show you where this comes from and how to find it on your calculator as well. The number of ways to select R items from a set of n different items total when the order of selection does matter, right? The order of selection does matter. It's called the number of permutations, and the notation is NPR. Or if you think about it this way, N pick R. I like to say P for pick. I have n objects, and I'm picking R of them and counting how many ways I can rearrange those R letters or R objects. The formula here is NPR, N pick R. The numerator is n factorial, right? The number of objects I have factorial, divided by then n minus r, the difference of these two little numbers. N minus r, take that difference, and then then the factorial of that. Right. And I'll show you how we can apply the fundamental counting principle to this. So, question. 7 city buses arrive at the bus garage around the same time each night, so like earlier. In how many ways can the buses return to the garage first, second, and third? All right. So new problem. So say we have 7 buses, right? And there are 7 different buses, right? So that's the n in this case. N is 7. There are 7 different objects I have. The question was, how many ways can the buses return to the garage first, second, and third? So like before, so the number of ways equals, and I'm going to use that fundamental counting principle. First I select, what bus comes in first. Then my next process is I select which bus comes in second. And then finally I select which bus comes in third. And we get all the possibilities by multiplying these, right? Three separate processes back to back to back. So if there are 7 buses, how many different ways could a bus come in to the garage first? So I have 7 choices of bus, right? So 7 for the first bus. But then once I select the bus that comes in first, once one of the buses comes in, then that bus can't be chosen anymore. So for the bus that comes in second, there are 6 possibilities. And then once these first 2 come in, they're off the table. And then for the third bus to come in, there are only 5 possibilities. And 7 times 6 times 5 is 210. So you could do it this way with the fundamental counting principle. I have 7 buses, and I'm trying to figure out how many permutations of 3 of them are there. That's the little r, that, remember the NPR, this NPR symbolism. N is the number of objects you have. R is the number of slots you're filling, the number of objects you're selecting. And I'm selecting 3 of them. So N would be 7 here. R would be 3. So this would be equal to 7 pick 3. Now I know what you're probably asking. Hey, that's not the formula that was given. The formula that was given was this thing. NPR, N pick R, is N factorial divided by N minus R, that quantity, factorial. You didn't use that. Why not? Well, because you don't have to. I showed you we can do it this way. But let me show you how this here, 7 times 6 times 5, is actually the same as our little formula. If you look at 7 times 6 times 5, and suppose I want to make this into a factorial. I'll give it a denominator as well. Now to make it into a factorial, I'd have to multiply by 4 factorial, wouldn't I? Because it would be 7 times 6 times 5 times, and then 4 times 3 times 2 times 1. And I can't just multiply the numerator by a number, right? I got it. Whatever I multiply the numerator by, I have to multiply the denominator by as well. So I put a 4 factorial in the denominator, and then this 7 times 6 times 5 becomes 7 factorial in the numerator and 4 factorial in the denominator, or 7 factorial divided by, and then 4 is just 7 minus 3. Right? 7 minus 3 factorial, and there's the same result I would have gotten using that formula. Okay. So I had 7 objects, and I was trying to see how many different orders could 3 of them come in. Right? N is 7, R is 3. Now, you can also find this on your calculator. So I'll slide this over, pull the calculator up. Now on the calculator, again back in the math area over to prob, you see NPR, number 2. Now on some of the newer calculators, you just hit it. Oh, okay. So some of the newer calculators, when you hit it, you can just enter the numbers, the N and the R. But looks like I have one of the older ones. Yeah. So what you have to do is you enter N first. So I have 7 objects, 7 buses. Then math, and then enter that NPR, and then the R. Right? So I have 7 objects, and I'm picking 3 of them. I'm trying to pick, how many orders can 3 of them, how many different orders can 3 of them come in? first, second, and third. And you see it's 210, like I got here, which was the 7 times 6 times 5, right? The 7 choices for the first bus, then you'd have 6 possibilities for the second bus, then you'd have 5 possibilities for the third bus. Same thing. Okay. All right, so that's counting permutations, counting how many different orders a selection of objects can come in. All right, so I go that here. All right, so some key terms, got the formula there. Let's get to another problem relating to permutations, right, where order matters. So there are 6 statistics instructors in the mathematics department at a college. If your major requires that you take 2 statistics classes, how many different ways can you have 2 different instructors for those classes? So yeah, now this time I'll pull up some paper on the screen. Okay, so this is, I have 6, n equals 6. 6 statistics professors are the objects I'm choosing from, right? 6 professors. R is 2, right? You're taking 2 classes. So think about it this way. You know, the number of different orders that the number of different ways you can select professors, number of orders, number of permutations is, you know, think about it. I'm filling 2 spots, selecting 2 classes, two professors. For the first class, I'd have 6 choices of professor. And then I select another class with a different professor, right? And so I wouldn't have all 6 to choose from, I'd just have 5. So I'd have 6 times 5, or 30 choices. There'd be 30 different orders, 30 different ways that I can have 2 different instructors for those classes. Now I could have also done this. 6p2. Right, I have 6 instructors, and I'm picking 2 of them, 2 different instructors. And then going through the formula, that would be, you know, 6 factorial divided by, and then 6 minus 2 is 4 factorial. And this would be exactly the same thing, right? Because if you think about it, 6 factorial is what? 6 times 5 times 4 factorial, right? Because you have 4 times 3 times 2 times 1. And then you have 4 factorial in the denominator, and then 4 factorial cancel, and I'm left with 6 times 5, or 30, as I had earlier. Okay. So there will be 30 different ways. Now they have you enter all these values, right? The number before the p is 6. The number, you know, the number of professors. The number after the p, the number of different professors I'm choosing is 2. That's the r. And then the number of permutations was 30. Right. Okay. So another one about permutations, where order matters. As part of a board game, players choose 5 unique symbols from 9 different symbols to create their secret password. Right, so definitely order is going to matter here, right? You know, one password, you know, ABCDE is going to be totally different than ABCDED, right, if I switch the order. So order matters. How many different ways can the players create a specific 5-symbol password? And it says give your answer in simplest form. All right, just basically write the number. All right. So again, I'll pull up a little piece of paper here. Hopefully it's not too bad. And you know, here we have 9 symbols to choose from. 9 different symbols. The key is that they're different. All right. We have the 9 different symbols to choose from. All right. And we're trying to select 5 of them, you know, put 5 of them in some order to make a password. So the R is 5. Right. So you can think about the number of different passwords that could possibly be created. Right, the number of passwords. Now you can think about it this way. I mean, this would be long. You're filling 5 spaces. Right, I write 5 little dashes. And this fundamental counting principle, you know, for the first symbol, I have 9 choices times, and then they're saying you have to use 5, different symbols. Can't use the same one. So once I've used a symbol, I can't use it again, meaning I have only 8 choices for the next symbol, and then I can't use these two, so then I have 7 choices times, and then 6 choices times, and then 5 choices. All right. You could also written this way. This is 9p5. 9 symbols, and I'm picking 5 of them to make a password out of. Right? And the order matters, obviously. It's a password. Or, 9 factorial divided by 9 minus 5 is 4. 4 factorial, which would be exactly the same as this guy up here. All right, now when I multiply this out, I'll enter it. All right, and I could probably do that in my mind, but I just don't feel like it right now. So let me pull the calculator up. I'll go to a paper here, pull the calculators up here. And I'll show you again how to enter that NPR. Right? I have 9 objects, 9 symbols. Go to math, over to prob, and NPR, and then I'm choosing 5 of those symbols. I'm picking, I'll say pick for P, permutations P, right? And you see it's 15,120. This is how I'll enter it, right? No commas, just go back here and let's get rid of the paper. 15,120 different passwords that could be created. And that's it. Let me go through the explanation here again. All right. So here we're given now this should be even easier, all right? Because this should actually be like, this is the first objective technically from this section, and I've already explained to you the fundamental counting principle. All right, but I'll go through it again. I'll read it to you. All right, a new objective. I'll click on more instruction. So remember, at times we may draw tree or Venn diagrams, as you saw in the previous section, or use contingency tables to help us calculate probabilities. You saw that in section 3.4. Sometimes there may be too many possible outcomes to reasonably create a diagram, right? You saw that again in section 3.5. If there were lots and lots and lots of choices, a tree diagram would be horrible to write, very, very tedious. So again, here's the fundamental. I'm going to skip some reading here and then get to the heart of it. All right. Now you've seen this before, and I've already been kind of demonstrating it to you already. The fundamental counting principle. So again, suppose a first event has A possible outcomes and a second event has B possible outcomes. Then the total number of different outcomes is A times B. This extends to any number of events, right? So if you have a third event happening right after the first two and it has C possible outcomes, then you just multiply by that, right? And you've seen me do it with more than 3, right? With the last example, right? This example here had 5 different events, choosing one symbol, then a second symbol, then a third symbol, then a fourth symbol, then a fifth symbol, right? So you've already seen me put this fundamental principle into action. All right, so I'll let you read that, and I'll go into some problems. And they go through factorial here, but I've already explained factorial. All right, so here, 4 companies have each sent 1 sales representative to a conference to pitch their newest tech products. The conference has 4 time slots designated for 1 sales representative to present their company's product. How many different ways can the representatives be ordered to present their products? All right, so again here, I just pull up some paper. There are 4 time slots. All right. There are 4 time slots. Think of it like this. And there are 4 companies, 4 representatives. So in the first slot, I have 4 choices of salesperson times, and then my next event is choosing the second salesperson to go. Can't have the same person who went first go again. So then there are only 3 choices times, then there are only 2 choices of the salesperson. Then there's only 1 choice at the end after the first 3 have gone. And this was that, 4 factorial, as you've seen earlier. If you have 4 objects, if you have n objects, the number of ways you can rearrange those objects, put them in different orders, is n factorial. And this is 24. Right, I had this up earlier. 4 factorial is 24. So there'd be 24 different ways of rearranging, putting these salesmen in different orders. All right. Continue on here. All right, here a standard deck of 52 cards. If you draw 1 card at a time from the deck without replacement, right, this has been discussed before as well, that means you pick a card and then you don't put it back. Right? You don't put it back. So once I've picked 1 card, then I'll have 51 cards in the deck. And I pick another card, I'll have 50 cards in the deck, and so on. How many different ways can you draw all of the cards? Remember that without replacement. I'm going to tell you that there. So that would be, now if you're talking about all the cards, right, that would be this. That would be 52, and I'm picking all the cards, 52p52, and putting them in some order, right? How many different orders can they come in? Remember how this goes. 52 factorial divided by 0 factorial, but remember what 0 factorial was? 0 factorial is 1, so this is simply 52 factorial, which again you could have told me without the p formula, because it's just basically telling me how many different orders can all 52 cards come in, right? And that'd be 52 factorial, which is a gigantic number, right? I bet it might even come up as an error on the calculator. I know that they did say put it in factorial notation, but let me show you. All right, 52 factorial is probably too big for the... Oh, it's huge. But it's... See this E67 means times 10 to the 67th power. That means 8 point, and then you move the decimal place to the right 67 places. This is a huge, huge number. But we're not putting that, right? They're asking us to... See, they say write your answer in factorial notation. So it's just simply 52... with an exclamation point after, right? 52 factorial. Another one. All right, now this one's probably on combinations. Looks like the objective's changing. Yes, counting with combinations. And this is the last of the 3 objectives in this section. Now you've seen the fundamental counting principle. You've seen counting with permutations. Right now, permutations, the order that things came in mattered. When you're counting combinations, you don't care about the order. Right? The order that things come in will not matter, and I'll show you in the more instruction. So computing probability involving combinations. So again, many interesting probability problems. Read that earlier. All right. In this section, we examine probability problems involving combinations. A combination is a grouping of items in a set where the order the items are chosen in does not matter. Right? The order doesn't matter with combinations. So for example, let's say we have a set of 3 elements, A, B, and C again, and we want to know how many combinations of 2 elements can we make from this set. So you could have A and B, A and C, or B and C. Those 3 combinations. Notice they didn't put A and B, then B, then A, because order doesn't matter when you're talking combinations. Right? Here we have 3 unique, 3 different combinations made of 2 elements from the set A, B, C. Since the order of the selection does not matter for combinations, we would not count a rearrangement of the same elements as a different arrangement. Right? That is, we would not list AB and BA because they both have the same elements. just rearranged, right? So combinations, you're not counting different rearrangements. You're just counting different groups of objects. So in this example, it was easy to list out the number, right? Just 3 of them, since we only have 3 elements. What happens if the set has 10 elements and we want to choose 2 of them? Or if it has 150 elements and we want to choose 100. Now notice earlier I said pick for permutations, P, pick, permutations, P. We're going to say choose for combinations, because you're going to see C showing up. C, choose, combination, right? The following formula will help us calculate combinations. Right? So it's just like the permutations formula, but with a little extra. So the number of ways to select R items, or choose R items at a time from n different items total, when the order of the selection, again, does not matter. It is called the number of combinations. And the notation is NCR, not NPR. So this is, usually I say N choose R. N choose R, and when it was NPR, I'd say N pick R. Right? So I have N objects, and I'm choosing R of them, and I don't care what order they come in. How many ways can that be done? That's what this calculates. So to calculate the number of combinations, we use the formula N choose R equals, the numerator is the same. It's N factorial, your number of objects factorial, divided by, and then you have the N minus R factorial in the denominator again, but also it's multiplied by R factorial. Right? There's this little extra factor of R factorial down here in the denominator. So don't forget that if you're doing combinations, if order doesn't matter. And also you may see this notation in some books. Combinations may also be denoted as, just a big set of parentheses with N over R like this, but no fraction bar, right? This isn't a fraction. If the fraction bar is not there, it means N choose R, or combination N objects. How many combinations of R can I pull out of those N objects? All right, so I'll let you read that example. Let's get to a problem. So here, a company sends 15 representatives to an industry conference. Only 11 will be given the chance to make presentations. How many different, combinations without repetition, right? Without repetition, meaning like the same person's not going to present twice. Right? You're going to have 11 different people presenting. So how many different combinations without repetition of 11 representatives are there? Now notice, it just said 11 will be given the chance to make presentations. It didn't say anything about in any particular order, right? Notice the word order or rearrangement or permutation wasn't mentioned here, right? So the order that they make presentations in does not matter. Okay. So in this case, the number of different ways that you can select presenters, as you had N, the number of objects was the 15 representatives. Right? There were 15 reps from a company. We're trying to select, we're trying to choose 11 of them, right? And the order doesn't matter. Right? The order that they come in does not matter. Right, so that's combinations. 15 choose 11. And to resort to the formula, the numerator, 15 factorial. Denominator. Now the denominator has two factors. One of them is that N minus R factorial. 15 minus 11 is 4 factorial times, and then the other one's just R factorial, 11 factorial, right? And if you add these up, they should be 15. 11 plus 4 should add to 15 up there. Now, if you're entering this in a calculator with the factorials, be careful. Make sure that you put this whole product in the denominator here in parentheses. Now we could do this by hand. this isn't too terrible, because I'd have what? This would be, well, actually the numbers are kind of big. I'd have 15 times 14 times 13 times 12 times, and then 11 factorial in the numerator. And then you got, that 11 factorial in the denominator times, 4 times 3 times 2 times 1, 4 factorial. And you got a lot of cancellations going on here. The 11 factorials would go, 4 times 3 is 12, so you can get rid of the 12. 2 goes into 14 7 times. So all I'm left with really is 15 times 7 times 13. Alright, so I'll enter that. 15 times 7 times 13. So 1,365. There'd be 1,365 different ways I could take 11 people out of 15. And again, it doesn't matter, just taking groups of 11, not caring what order they come in. So there's 1,365 different groups of 11 you could make out of 15 people. Now, you might say, I don't feel like doing all that with the simplifying and whatnot. So again, you can do this on the calculator as well. There was an NPR on the calculator. There's also an NCR. Now again, I have one of those where you have to enter the N first. So I got, I'll enter 15. Got 15 objects. And hit the math button. Go over to the prob. Then you see under NPR is NCR. I enter that. And then you enter the R, right? How many objects you're selecting. We're selecting 11 of these people. So 15, NCR, 11, and you see it's the same number, 1,365. So that's what I'll be entering back here. Right? So how many different combinations of 11 representatives are there? 1,365. All right. Great. Okay, let me go through the whole formula again. Alright, now what about multiple combinations? Now this is again applying the fundamental principle, but this time at each stage, at each event, we're going to use combinations to count. Alright, you'll see what I mean in a minute. So let's go to a problem. Alright. So here. 2 classroom teachers are choosing 15 students to participate in a school-wide event. The first teacher chooses 7 students from the 21 students in her class. The second teacher chooses 8 students from the 23 students in her class. So we got to fill in the blanks down here, but I'll write it on paper. I'll show you. Use the template below to show the notation for calculating the number of possible combinations without repetition, right? Just how many groups, how many combinations of 15 students could be selected from these classes if they're selecting them this way. All right, so I'm pulling up the paper. All right. We have 2 events, right? There are 2 events here. One, the first event is, the first teacher selects her students. And then we'll multiply that by the number of outcomes of the second event. And the second event is that second teacher selecting her students, the 8 students out of her 23 student class. So the second teacher selects. And then each one of these is their own separate combination problem, their own separate combination event. Think about it. How many outcomes are there for this first event? How many different ways can that first teacher choose 7 students from the 21 in her class? That would be 21 choose 7, right? Because it doesn't matter what order they come in, right? She's just selecting a group of 7 students without the order mattering out of the 21 in her class. So the number of ways this first event can happen is 21 choose 7. And that gets multiplied by the number of ways the second event can happen, right? And this second event is, the second teacher selects her students. And how many ways can she do that? Well, she's choosing 8 students out of 23. So it's 23 choose 8. And I can enter this in my calculator. Let me pull this up on make it bigger. So that I have, I'll put it in parentheses, the first event, the number of ways that can happen. 21 choose 7. That's the number of ways the first event can happen. The first teacher can choose her students, 7 students, times, and then the number of ways the second teacher can choose hers, right? The 23 choose 8, right? And that's a gigantic number. Huge, right? That means move the decimal place to the right 10 places. But we're not asked to put that. We're just asked to fill in the blanks for the NCRs, for the combination notation. So the first choice, right, we have 21 choose 7. Right, 20. I just filled 21 and 7. Then the second teacher, the second event, multiply that by she has 23 choose 8 choices. Right, so I fill all that in, and that's all I want. Right. Alright, so now we're back to just the fundamental counting principle, which you may have noticed has been used throughout all this section and all the objectives. So suppose a bag of colored marbles contains 15 marbles. If you draw 1 marble at a time from the bag without replacement, right, you don't put it back, how many different ways can you draw all the marbles from the bag? So that's the 15 factorial. That's just like put factorial notation. That's just like the drawing the cards earlier, right? And they want all of them. That's 15 pick 15 or 15 factorial. So I'm just writing 15 factorial with the exclamation point there. Simple enough. Another one on the counting principle. And you suppose that 10 unique names are put into a hat and drawn at random without replacement. How many different ways can you draw all the names? So that's 10 pick 10, 10p10, or just 10 factorial. Right? It says how many different ways can you pick all, draw the names from the hat. That's, order will matter there, because picking James then John is different than picking John then James. The order matters. So it's definitely a permutation problem. And 10p10, as I mentioned, is just 10 factorial. So I believe that objective's done. Yes. And then we got another permutation. Order matters. 12 new students are standing in a line. How many different ways can the first 7 students in the line order themselves? So this would be 12 pick 7. All right. 12 students. How many different ways can we rearrange the first? How many different ways can we put the fill the first 7 places in line? Order will matter there, right? 12, pick 7, and I'll bring the calculator up for this one. So that's 12, then the NPR 7. So 3,991,680 different ways that you could place the first 7 students. So 3,991,680. Oop, I put 15. 16. Okay, wonderful. All right, another permutation problem. So that you're going to notice again the order that things come in will matter. You are planning a road trip and there are 15 different cities you would like to visit. Due to time constraints, you can only visit 4 of them. If you do not want to repeat any of the cities, how many different ways can you visit 4 of the 15 cities you are interested in? So again, the order matters because that'll determine your trip, right? The order you want to visit the cities in matters because that'll determine what paths you take. How do you travel? So this is definitely a permutation problem. So I got the 15 cities, and I'm picking 4 of them to visit in some specific order. 15p4. So again, that'd be the 15 times 14 times 13 times 12. Right, 15p4 for filling 4 slots. I'm pulling the calculator up. 15, the NPR 4. So 32,760 different ways I could visit 4 of those 15 cities in some specific order. Oops, I want to put the calculator up there. All right. Wonderful. And then the last problems should just be on counting with combinations. And I see the word combinations again. You're choosing groups. You're not worried about different ways, different orders. Okay. Order doesn't matter. So a swimming team has 16 members. The coach wants to create teams of 4, right, to complete the relay race. How many different teams of 4 can she make without repeating a team, right, without repetition? So again, just making a team of 4 swimmers, the order that those people are in doesn't matter. If I have a team with James, Bob, Joe, Frank, having Frank, Bob, Joe, and James is the same team. It doesn't matter what order they come in. So this is 16, choose 4. All right, so again, I'm pulling the calculator up. I have 16 swimmers, and I'm choosing 4 of them, without picking the same person twice, right? Without repetition. And that's how many different teams of 4 people I can make. 1,820. All right. There should be one more here. And last one, looks like this will be the last one. So another combination one, right? The order, again, try to read into it, try to figure out, why doesn't the order matter, right? The order shouldn't matter here. A donut shop makes 21 different types of donuts each day. Customers often select a baker's dozen from the shop. That is, 13 donuts. How many different ways can a customer choose 13 different types of donut for their baker's dozen? Without repetition, right? So basically 13 different kinds of donut from these 21. And again, it wouldn't matter what order. If you had a chocolate glazed and a Boston cream, it wouldn't matter if it was Boston cream then chocolate glazed, right? They're still in the same box. So the order doesn't matter. So this is another one where you're doing combinations. So I have 21 types of donut, and I'm choosing, right, NCR, 13 of those types to go in my baker's dozen. And there's 203,490 ways to do that. 490 possibilities there. Okay. All right, so again, just pay attention to what's what. Are you talking permutations? Does the order matter? Or are you talking combinations? Does the order not matter? And don't forget also what that fundamental counting principle states. Right? If you have so many events happening back to back to back, you're making so many choices back to back, the total number of possibilities is the product. You multiply the number of possibilities at each step. Alright, so hopefully this video is a good guide for you when you go through this assignment on your own. Obviously, if you have any questions, send them to me, let me know. And thank you very much for watching.